In this problem, an object falls the distance h from rest. If it travels 0.5 h in the last 1 second, find the time it takes to fall and the height of its fall. Let's draw a picture of this situation. Let's say that we have a ground here, and the object starts up here. So I'm going to say that up is positive, and I'm going to say that this is my initial position, which is this is my origin, which is x equals 0. We also know that there is a height here of h, which is given to us. And we're given some information about h over 2. So when the object is halfway down, and this is h over 2, then we've got some information about the time that takes. So there's my situation. When the ball is up here at the top, we're going to call that our initial position. So I'm going to put x initial and also our initial time. And our initial time is going to be 0. So I'm going to set that there. Then when the ball is at h over 2, we're going to call that x1 for position 1. And that's going to be time 1 as well. And then when it's at the bottom, we're going to call that x final and time final. Now we know from the problem that the last part of the motion of the ball, when it falls that last h over 2, that takes 1 second. So we know that t final minus t1 is equal to 1 second. We also know that the initial velocity of the ball, when it's up here, we'll call this v initial, is equal to 0. So I'm going to look at this in several different portions. We're going to first focus on this first part right here. And we're going to see if we can write an equation for that. Now I know that the change in position of the object is equal to the initial velocity times time plus 1/2 times the acceleration times time squared. Because this object is accelerating at a constant rate, I guess we also know that the acceleration is negative 9.8 meters per second squared. In this first portion, the initial velocity is 0, so this term goes away. And then I can start plugging in some things. So our change in position is going to be x final minus x initial. So that's x1 minus xi. And that is equal to 1/2 times the acceleration times time squared. And time squared is final time minus initial time. So that's t1 minus t initial squared. I do know that t initial is 0. So I can do that. And I know that x1 minus x2 is h over 2. Because if the bottom part's h over 2, the whole thing is h, then this part must be h over 2 as well. So I can write h over 2 is equal to 1/2 times our acceleration times t1 squared. We can simplify that, and we're going to solve for t, and the reason we do that will become apparent later. So this gives us t1 is equal to the square root of h over a. So we've got an equation for our time for the first part of motion. Now we need another equation because we don't know time and we don't know h. We do know a, but we've got 2 unknowns, so we're going to need 2 equations. We could look at the bottom portion of motion. The problem with that is that we don't know how fast the object is going when it hits h over 2. And so instead, I'm going to expand and I'm going to look at this portion of motion together and make an equation for that portion of motion because I know the initial velocity is equal to 0. So when we're looking at that portion of motion, we know that let me change this real fast. we know several things. We know the initial velocity is 0. We know that the time is our total time, and we know the distance that it falls is h. So let's use our same equation from up above. Delta x is equal to v initial t plus 1/2 at squared. And our v initial t goes away because our initial velocity is 0 at the top. I should probably write that on our little knowns chart. Then we know that our delta x is just h, right? Because it falls that entire distance. And we know that we have 1/2 at squared, and our t is going to be t final minus t initial, and t initial is 0. So I'm skipping a step here. I showed you the step on the last one, but I'm just skipping it. So that is t final squared. Now let's solve for t final. So we get t final is equal to 2h over a, and that is all square rooted. All right, so I've got t1 over t final, and I know that t1 and t final are related with this equation over here. So I'm going to do something kind of slick. I have this square root and the h in there with the a, and so I'm going to combine those together. I'm going to say that t1 over tf is equal to the square root of h over a, so that's my equation for t1, divided by the square root of 2h over a. So you should notice here that our a's cancel, our h's cancel, and what we're left with is the square root of 1/2. So I know that t1 over tf is equal to the square root of 1/2, and I also know that tf minus t1 is equal to 1 second. So I've got two equations in two variables, and I can pretty easily solve this now. So let's say that the square root of 1/2 is equal to t1 over tf, and I'm going to solve this equation for t1, that top equation. So t1 is equal to tf minus 1 second. And then I'm going to plug that into this equation over here. So we have t final minus 1 second over t final. And now we've just got a little bit of algebra, and we should be able to find that t final is equal to 3.4 seconds. So we know that the total time for the object to fall was 3.4 seconds. And then we also needed to find the height of the object's fall. So once you have the time, it's pretty easy. We know delta x, the total delta x, is equal to v initial t plus 1/2 at squared. And we're looking for delta x. We know our initial velocity was 0, so we just do 1/2 times acceleration, which is negative 9.8 meters per second squared, times time squared, so 3.4 seconds squared, and we get 56.6 meters. We can double check our units. We have meters per second squared times seconds squared. Our seconds squared cancel, and we're left with meters. So that works out well. So let's zoom out on this so that you can see it all together. And that is how you solve that problem.